All right, so here in 13.2, we're talking about simple harmonic motion. The most common example, and what this was usually comes from, is a mass attached to a spring. All right, where we basically have it being frictionless or really close to frictionless. And essentially, if you want to know if something is in simple harmonic motion, you really want to know if it matches that equation that is right here, this one right there. All right, that is what is called Hooke's law. And if it fits that equation, it is simple harmonic motion. And some of the properties you can see of simple harmonic motion is that it will have an amplitude. And at its amplitude, it will be going its slowest. It will have an equilibrium position, which is what it's like going back to. And it's going between these things. At its equilibrium position, it's going to be going its fastest. And your force is going to be proportional and in the opposite direction. That's what that negative sign is. Some constant K, depending on how strong of a force it is, and then the further away it is from that equilibrium position is measured by X there, and you will have simple harmonic motion. All right, so if you're asked whether or not something is simple harmonic motion, you just have to see if it fits that equation. If it does, then it is. In this case, a mass on a spring will fit this equation. The further you stretch the spring, the stronger it's going to get and the more force it's going to pull back with. And if you stretch it to the right, it's going to pull it back to the left. Or for y'all to the left, it's going to pull it back to the right. And if you stretch it or compress it, you know, one way, it's going to want to push back the opposite way. And it's going to want to try and get back to that position where it's not stretched or compressed at all. That's where your equilibrium position is. All right. So let's take another example here. Let's say I were to start a ball bouncing, and this ball didn't lose any energy as it bounced, and so it bounced up to the same height every time. Is that ball going to be bouncing in simple harmonic motion? Yep, same height every time. Sure seems like it, right? What do we got? We've got a maximum amplitude, right? Where is that? It's height it goes, right? Do we have an equilibrium position? Where we could put it where it wouldn't be doing anything if we just put it there? The ground, right? That's also, I said, where the equilibrium position was where it's going to be going the fastest, right? And as it falls down, the fastest it's going is down at the ground, right? And then at the amplitude, we said it would be going the slowest at where it got. Y'all said that was at its highest point, right? It's the maximum it gets away from the equilibrium. It'd be going zero essentially there. And that's also, it's going to go no speed there. It's zero at the highest point. Y'all should have learned that last semester, right? Or a few years ago. Okay. It's at that point. So this sure looks like simple harmonic motion, right? And what do you guess I'm going to tell you right now? It's not. Anybody able to tell me why it's not? Why not? Every time I let it go, it's drawn back down to the ground. If it goes up, the force pulls it back down. Yeah. No, I don't think so. I think our amplitudes are always positive. They're like an absolute value. It's like a distance. It's not really a displacement. X is a displacement. The amplitude is just maximum of it, positive or negative. I don't think that'll do it. Yeah. Oh. I mean, we could do that with the spring, right? Depending on how far I pull it or let it go. Yeah. Because it's bouncing the same height each time. No, because if we're doing this, this is gonna swing the same amount each time, as long as we're not losing energy. Any other ideas? Once you hear it, you're gonna think, "Oh wow, that was really obvious." Yeah. Say that one more time.
The ball is dropping down because of gravity, but the spring is not really dropping.
We can have some, we'll do a pendulum, which we'll say is simple harmonic motion, and that's due to gravity. So it doesn't have to necessarily be just a spring for simple harmonic motion.
It bounces instead of.
No?
The restoring force isn't proportional.
Exactly. There you go. The restoring force is not proportional to the displacement. Right? Think about this. The further you pull a spring, The more you stretch it, the harder it gets to stretch it, right? The more you compress it, the harder it gets to compress it. If I keep lifting a ball higher and higher and higher and higher, does gravity on it get stronger? If I take it up to like 100 miles up, is the gravity stronger up there than down here? No. In fact, the higher it goes, the weaker the force of attraction gets for it. So it may look like simple harmonic motion, but it's not, because the restoring force in that situation is 1 over the distance squared. All right. So that's not it at all. Okay. Y'all did gravity, didn't you? 1 over, F equals G M1 M2 over R squared from the center of the earth. Right? You didn't do that? Oh, all right. Okay, then Newton's law of universal gravitation. There we go. Okay, so you have to be careful. Sometimes things look like it, but it has to fit everything, including that idea that the restoring force is proportional to the displacement, not proportional to the displacement squared, not inversely proportional to displacement or inversely proportional to displacement squared or anything like that. Okay, here is what you can see is some simple harmonic motion here, and you can see that this is very much related to what's being drawn out above it. So you could imagine what they're doing here is like they took a mass on a spring and they let it bounce back and forth and they hooked like a marker to it. And as it goes back and forth, they're pulling a piece of paper through underneath it at a steady pace. Okay? And what's it going to draw out? It's just a sine wave, right? In fact, it's going to be exactly a sine wave. So you end up having this simple harmonic motion being very much related to sines and cosines. Okay, very much related to it. And here you can see that the amplitude is that maximum distance it gets away from equilibrium. So this equilibrium position is this right here in the middle. And so this is the amplitude, or this is the amplitude, right? So the amplitude is always positive. That's why they put that negative A over there for the position. Okay, we always count that amplitude as positive. All right, they're marking the position as negative of the amplitude. All right, but it's not that whole thing. It's not from maximum displacement in one direction to maximum displacement in the other. It's from that equilibrium out to the maximum. So be very careful with that one. Okay, and so it's very, very close to this. I think I have a marker. So hopefully it still works. So, and you can see this here. If I start like this, right? And I think if some of y'all had me for calculus, I probably already did this, but I start here and I'm doing simple harmonic motion, just bouncing back and forth, right? But if I start walking this way as I do it, right? What do I end up drawing? Nice sine wave, right? And all you do is just keep that same motion going. Okay. So there's that. Simple harmonic motion goes right in with sines and cosines. So there's already a big relationship between simple harmonic motion and waves. Now, what you can do here is this actually will come right out of Hooke's law. If you really want to see it, I don't know that I have a lot of time to show it to you, but if you ever do really want to see it, email me. I'm always happy to show the stuff that I think is really, really neat. It takes some calculus, but basically the idea here is if you look at Hooke's law, I can just give you a little hint on it, but everything we're about to do all just falls right out of Hooke's law here, right? Negative kx. What does F equal? What does it equal? Not what is it? What does it equal? Newton's second law. I know you know it. MA, right? It's MA. MA negative kx squared. For those of you who've taken calculus or even just from last time, how does acceleration relate to position? Second derivative, right? It's two derivatives of it, which means this is m times the second derivative of your position, right? Equals negative kx. And so what we can say here is d2x over dt squared, if you haven't taken calculus, then sorry, equals negative k over m, and remember that negative k over m right there, times x. And so what we're looking at here is what you should see, and I need to start writing a little bigger, I think. But what you can see is we have a second derivative of something equals to the negative of some constant, K being just some constant. It's called the spring constant. It tells you how strong the spring is. And then the mass you have attached to it, unless you're like changing the mass out as it's swinging, otherwise those are constants. So we need some sort of function that when you take the second derivative of it, gives you back the negative times a constant times what you originally started with. Can anybody think of a function that does that? What's that? Oh, come on. Sine and cosines, right? Right? If you did the derivative of cosine of omega t, the first derivative would be what? What's the derivative of cosine? Negative sine. And then we have to chain rule it, right? So it's negative omega sine omega t. And then you have to do the second derivative. So that's the first derivative, right? Like we can say this is x, which we have right here, right? There's x. We have x equals that. This would be the velocity. And then we do one more derivative. And what do we have? Derivative of sine is cosine. So we end up with negative and then chain rule omega squared sine of omega t. Oh, I meant cosine, sorry. I'm used to doing these as sine waves, but they're doing it as a cosine, which is fine. That just means you're starting with the displacement. Really, you should do a sine plus a cosine. And then it accounts for any possible situation, but this one is a special case. Okay? And so there you see, sines and cosines, they fit that. We have what we started with, the cosine omega t, cosine omega t. We have a negative, and then we have that right there, which also then tells us that omega, right here, this omega squared has to be that negative k over m. So that just means then that omega, that wasn't a very good omega, omega equals square root of k over m. All right, and we're going to see that here in just a bit. And it also, of course, is going to equal 2 pi f. Another thing omega equals 2 pi f. Omega is what is called your angular frequency, okay, or angular velocity. It's related to frequency by just a conversion of units, okay? If you just think about this, frequency is your number of cycles per unit time, whereas the other one is your number of radians per unit time. That's what omega is, it's radians per time. So if you do a unit conversion, you end up multiplying by 2 pi, and that's why omega equals 2 pi f. Just by simply converting units. They're the same thing with different units. All right, you convert the radians to cycles, and that's what you get. And then, of course, frequency, how did we say earlier it's related to period? It's the inverse, which means we can also say then that omega equals 2 pi over the period, which is what they have right there in that equation. A cosine 2 pi t over the period. And then what's that A? Amplitude, right? The one we did right down here would have just had an amplitude of 1, which is what cosine goes between 1 and -1, right? And then you just scale that up. Make it an amplitude of 2, you multiply it by 2, it's going to go between 2 and -2 from your sines and cosines, from your trig days, right? All right, everybody see that? Okay. Any questions on that? Good. All right, take a look here. Connections between uniform circular motion and simple harmonic motion. So the first connection we did was simple harmonic motion connected straight with waves, right? Now it also connects with uniform circular motion. And normally I have a projector in my rooms to do this. But the idea is, if you could imagine this for a moment, if I had like like a ball or something I was holding here, and we had a light shining up on here. The ball would cast a shadow, a circle onto the board, right? And if I started moving the ball in a just constant circular motion, its shadow would just move up and down, correct? Because I would just go up and down. It's just projected onto the wall. Y'all agree with me? That shadow would just go up and down? That shadow would go up and down, yes, exactly. And it would move perfectly in simple harmonic motion. It would follow all this stuff. And that's what they're showing you here in this picture. They've got these pegs on there, and as the pegs rotate around and go in the opposite direction of the arrow indicating there. So I shouldn't do that. But as it goes around, what they're showing you here is you can see the little shadow is just going to move back and forth, and then they've put a mass on a spring, and if they were in the same exact simple harmonic motion, they would just stay perfectly aligned, right? The shadow and the spring would stay right there together with each other, assuming they have the same frequency. Okay, if you spun that record at the same frequency and amplitude as that spring, then its shadow of that peg would stay perfectly in line with it, right? I didn't do that very well, right? Ooh, like that, where one of them is simple harmonic and one is circular. So it's pretty neat, and it's pretty nice that all of this math that we're doing here for this, it works for all three things. It works for waves, it works for simple harmonic motion, straight line back and forth, and it works for circular motion. Okay? So all three of these things are all very connected, and the math really overlaps. You can have a period and an amplitude for simple harmonic motion, for waves, and for circular motion. Periods and frequencies. Okay, and then here, this is, again, the uniform circular motion and simple harmonic motion. And this one I already just did a few pages back, right? I told you that omega was that 2 pi f just by a change of variables, right? By the way, if you want to change variables on something, if you want to change its variables, like convert it from meters to miles or something like that, how do you do it? What do you multiply by every time? This is like always my favorite answer. You'll learn this, hopefully. There you go, you remember that, huh? You're gonna multiply it by 1, okay? Ultimately, that's what you're doing. And so if I wanna convert something like radians per second into cycles per second, I have to multiply it by 1 cycle is 2 pi radians, something like that, right? And since these two things are the same, that second number there is just the number 1, right? Okay. So just kind of look for that. When you do these conversions, you should notice that all the factors you're multiplying by, if you're writing the units in, which you should do all the time, they always equal 1. It's just something divided by itself. If it doesn't equal 1, then you're doing something wrong. You're not just converting units, you're changing the actual value there, okay? So be careful of that. All right, and so this was that, and then we also said this was 2 pi f. And again, that 2 pi shows up from converting the frequency of cycles per second to radians per second, because they're 2 pi radians. All right, we good so far? All right, so let's go back and let's take a look at some examples here. So let's take a look at this one. 2 baseball players warm up with a game of catch. If it takes 6.6 seconds for the ball to go from one player to the other and then back to the first, what is the frequency of the ball's motion? Go ahead and try that one. I'm going to pause. So if we're looking at this, they're giving us time, correct? And they're giving us the time for what? Are they? Are they giving us the time for 1 full cycle? It's half a cycle. It's only from one of them to the other, right? So they're giving us t over 2 is 6.6 seconds, correct? And what are we trying to find? Frequency. We're trying to find frequency. All right. So what is a relationship between frequency and time? Yep. We know that frequency is 1 over the period. So if we can get the period, we can take the reciprocal and get the time. Thankfully, we've got this right here. This tells us that this equals 2 times 6.6 seconds. Always write your units the whole way through. Use your algebra on them, which is what? 13.2 seconds. Okay. And so this just becomes 1 over 13.2 seconds, which turns out to be about what? 0.08 hertz. Casey, is that right? Okay. All right. Any questions on that? Yep.
Can you explain how it's T over 2?
Because it's 2 people, right? So this one and this one, and they told us the amount of time it takes for the ball to do that. A full cycle. Oh, I thought that meant 6.6 from one to the other, and then. Yes, it is. That was for you, Emily. Okay, we can do that. I'm sorry. How about that? How about that? There we go. Is that better?
Yeah.
Woo. That's fine.
Would you say it was more just like an interpretation?
I don't know. I thought that's what it meant. If it takes, I mean, I guess they say and then back again. Like, yeah, no, you're probably right. I was probably wrong.
So since it's the same process, we have like a question like that on an exam.
Yes,
Like,
you'd want to.
especially if we're doing it online. How are we supposed to-
I think you're right. I think I just misread it.
Okay.
That's all I think it is. I don't think this is that ambiguous as I originally thought. I just read it too quickly. Don't be me. Be better at language than me. How about that? I think anybody that had me before knows that's my great weakness. All right. So how about this one? On an air track cart attached to a spring, completes 1 oscillation every 2.4 seconds. At t equals 0, the cart is released from rest at a distance of 0.1 meters from its equilibrium position. What is the position of the cart at A, 0.3 seconds, B, 0.6 seconds, C, 2.7 seconds, and D, 3 seconds? So for this one, because we're getting a little short on time here, I'm going to just go through this with you. So it's attached to a spring. So what kind of motion is this going to be? What is it? Simple harmonic. And do we have some sort of equation that fits simple harmonic motion? What was it? That's right. It was, where was it? Right there. Right? So A times cosine of that omega t there. The way I really prefer to remember that one as A cosine omega t. I just think that's a little simpler version, but then you have to know what omega is, or understand what it is. Okay, so we come back over here and we say it's simple harmonic motion. So the position as a function of time is governed by A, the amplitude, times the cosine of, and what do we have here? Time t is released from rest. 1 oscillation every 2.4 seconds. So what is that? Period, right? So we can say here we've got omega t, which is just A cosine 2 pi ft, and then it's also the same thing as A cosine 2 pi over t times the time, like that. And that's the one given to us. And so they're telling us it's 2.4 seconds. So given is the period is 2.4 seconds. It is also told us that at time t equals 0, the cart is released from rest at a distance of 0.1 meters. Now, if we release it from 0.1 meters, is it ever going to get further away than that? Releasing it from rest. Y'all did energy last semester, right? So can it, if I drop a ball, just drop it, not throw it down. If I throw it down, I can get it to bounce out. But if I just drop it, is it ever going to bounce up higher than where I let it go from? So if I just release that spring, is it ever going to get further away than that? So what is that 0.1 meters? It's the amplitude. It's the maximum that's going to get away from there. So the amplitude is 0.1 meters. And so to do these, you can say, all right, let's look at part A. We have the period, we have the amplitude, and we're given in a certain amount of time. So we would say X as a function of, what do we want here? 0.3 seconds. 0.3 seconds is equal to the amplitude, 0.1 meters, times the cosine of 2 pi over 2.4 seconds times 0.3 seconds, like that. Plug that all in, and that would be your answer.
Is there, I'm sorry, I'm kind of confused by the times on both sides.
That's a function of that. Like X is a function of T, but we're putting in 0.3, right? You know how you do like F of X and then you do F of 2 or F of 7. Yeah, that's it's just my notation I was using. You don't have to use it if you don't like it. You can just put X equals. And then you can go through and do the same thing for the other ones, right? B X equals, and here again, 0.1 meters, cosine 2 pi over 2.4 seconds, and then just change this to 0.6 seconds, right? All we're doing here is changing the T. Everything else is a constant for this problem. The amplitude's a constant, the period's a constant, we're just changing T, okay? And you should go through and do these, plug them each in and see what values you get. You know, just because one of them is the longest amount of time, like 3 seconds or 2.7 seconds, those ones, does not necessarily mean you're gonna get the biggest, you're gonna get the largest displacement there. Its position won't necessarily be furthest from equilibrium. Okay? All right, so y'all can do this on your own. Do y'all have that copied down? It should be backed up on the notes online too. You can go in there and look at them, okay? So take a look there. All right, let's keep going here. So there was that. We connected it to the circular motion. And then here you go, here it is again, connections between this, there it is all put together. A cosine theta equals A cosine omega t, which is A cosine, and then I added that one extra one in there where I use this 2 pi f, right? At an A cosine 2 pi f, what I just wrote, this part right here, right? That's what they're showing you right there. It's just all of that. And it all just kind of falls together. That's the wonderful thing about all this physics and stuff, is it really does follow these rules. It's amazing to me, you know, like anytime you ever see something that is organized, right? It has a creator, isn't it? Like who walks along in the woods? Like every time you've ever seen a bull come into existence, somebody sat there and made it, right? If you're walking along the woods and you find a bull, you don't think, oh, look, a bull just randomly formed here in the woods, right? You think somebody made this bull and left it here, right? Because it has rules and it has this order to it. Our whole universe has rules and orders to it. Creator, scientifically, right? We look for correlations.
I can't hear if it's a bowl or bowl.
Bowl, B-O-W-L, like a bowl. No, not a bull. You thought that too? Someone created a bowl, you found out there. Bowl. Okay, a fork. Do y'all hear that one? Spoon. You find something that every time you've ever seen, every time you've watched how it's made, you saw someone do it, you know, and, you know, you find it and you think someone made it. You don't think, hey, look, randomly that formed. So anyway, any questions on this? Doing okay so far? Okay. All right, how about connections here between these two? Now this one I already did as well, a little bit. I just didn't have the A's in there, right? A omega, the negative A omega sine, and the negative A omega squared cosine, right? That was what I did right there, down at the bottom. That's these, where we just took derivatives of it. So if you've done calculus, if you're fairly clever and you've done calculus, honestly, if you're going to do any of this, all you really need to remember is Hooke's law. In fact, that's all I ever remember. Every time I sit down, like I'm sure if you asked me to do this later today, I'd just remember these off the top of my head. But if I didn't do this for a year and you said, solve this spring problem, I'd remember F equals negative KX and I'd sit here and just start deriving all of this out. Okay, it is far better to understand than to memorize if you can. So it's one of those things. Physics with calculus is easier. So if you're asked to do the same thing in physics with calculus versus algebraically, it's easier with calculus. But if you go take a calculus-based physics course, is it easier? No, because it just means they can give you harder problems, right? So it's not any easier. But if you attack like this class and you have some calculus in you, you can make this class easier with it. Okay? Yeah.
Will we have more components for the exam?
Yes. Yes, you will. All right. Yeah.
Does that velocity have acceleration angular or no?
That omega?
The velocity in the
No. So that velocity is linear velocity, right? Such that, what do you have? Did y'all do rotational motion? And you did stuff like L equals theta R in radians, and then V equals omega times R, and A equals omega times R, all those, and then like you could replace like if you had F equals MA, it becomes torque equals I alpha. Oh, I wrote an omega there. That should have been an alpha. Sorry. Right, you did that kind of stuff. Yeah, it's pretty neat. All the linear stuff, you just swap it out for its rotational counterpart and all your formulas still work. Yeah, that's fun. But yes, that's the linear version. If we were talking about circular stuff, it'd be the tangential one, the tangential velocity. And then omega is the angular velocity, radians per unit time. Is radians an actual unit? No, you can kind of just throw it away whenever you don't want it. We just kind of use it there, but it's not actually a unit, it's a ratio. That's what radians are. Okay. 13.4, the period of a mass in spring. There's that square root of K over M, that omega equals square root of K over M, which I did a few pages back, told you to remember it, right? There it is. Omega equals square root of K over M. And if we go through, because those were in that same place, we have that omega squared equals K over M, and we said omega equals K over M, so we already did that. This is your period then, because that's right where it fits in, right? We said omega equals square root of K over M, and omega also equals 2 pi over the period, because it was 2 pi f, which means we can do multiply both sides by t, right? Divide by this, so we get t is equal to 2 pi square root of m over k. And that's your formula for the period of a mass spring system. And again, this just falls out from F equals negative kx. I mean, that's all we've really done so far. It's just that and some ideas of angular motion, right? we did f equals negative kx, did some calculus on it, and then just math, and then unit conversion, and we're there. And a couple of our definition of what period and frequency are. And there you have it. Okay, so that's what your period is going to equal, and the period is the amount of time it takes for it to repeat once. If you look at these little graphs here, you can see they are position as a function of time, and so the period would be from here to here. It would be that amount of time. That would be, this would be one period. It could also be from here over to here. It's just however long it takes for it to repeat, right? That's a period as well. Okay. 2 pi that. Any guesses on what an equation for the frequency would be? Yeah, flip it over, right? Frequency 1 over 2 pi square root of k over m instead of m over k. If you know the period, you got the frequency. If you got the frequency, you know the period. Just reciprocals, right? Don't make it complicated. Don't remember both of those. Remember one of them and take the reciprocal. Okay? Cut your memorization in half. And then here we have conservation in oscillatory motion, but let's actually go over and do a problem here for 13.4 instead of getting there. So let's take a look at this. As an example 13-3, an air track cart attached to a spring completes one oscillation every 2.4 seconds. So immediately, what did they tell us right there? Period. So we might as well write that down. T equals 2.4 seconds. That's a given. At time t equals 0, the cart is released from rest with the string spread. Wait, is this the same one? No. This is what is the velocity and acceleration. So again, it is stretched and released from that same amount. So what are they telling us there? Amplitude. So we have an amplitude equal to, what was it, 0.1 meters. We're not in lab right now, so I'm not worrying about significant figures. Okay, in there we will. Are you all taking lab? Everybody? Okay. If you're in lab with me, remind me to ask if everybody in lab is in here, because I feel like this morning I sent like 4 things out to everybody, sending it out, the same notice to the same reminder to lab as an announcement and as an email, and then to this class as an announcement and as an email. And that's like, I feel like I sent the same thing to y'all 4 times, right? Is it okay if I just do announcements, not emails? Be sure you're checking your announcements. Make sure you have the notification set up so you see announcements. So then I'm not dubbing. So that cuts it down to 2. And if everybody that's in lab is also in here, then I can even just say, maybe I'll just send it out just here, unless it's like specific to lab, okay? All right, so the amplitude is 0.1 meters. So what are the velocity and acceleration of the cart? So if we look at part A, we wanna find the velocity and we wanna find the acceleration. So who can tell me what the equation for velocity was? We can write these all down. Position was what? Good, cosine. 2 pi over t, capital T, right? Times what? Times little t. Good, there we go. So then what's the velocity? Nope. So let's do that. Let's change this from 2 pi t. Let's make it omega. Omega t. Omega sine. Good. And then acceleration. Good. How many of you have taken calculus? So most of you. It's hard to remember, but at least you have some idea what I'm saying. It's not like total nonsense when I say derivative. You remember hearing that word before, right? How to do it? Not necessarily. But it was like a slope, right? It was a slope thing. There you go. As long as you got that part. Conceptually. Go hop on 3 Blue 1 Brown and watch that first like video of the fundamentals or whatever it is, the essentials of calculus or whatever they do. Take a few minutes and watch it. They're really good anyway. So that's what we have. And of course, omega equals 2 pi f, which is 2 pi over t. And we have t here. So this is, and then we'll also make use of this. Omega is 2 pi over t. All right. And so to get the velocity for part A, we're just going to plug that in. So everywhere there's an omega, we'll write 2 pi over t and go from there. So this is going to be v equals negative a, and then we'll make 2 pi over the period sine 2 pi over t, little t like that. And you can plug your numbers in then. So this is the amplitude is, so negative 0.1 meters times 2 pi over 2.4 seconds times the sine of 2 pi over 2.4 seconds times our time here. We wanted what? 0.3 seconds, just like that. Plug that all in, hit equal in your calculator, all right? And then for the acceleration, and I'll let you do part B your own selves with that. Again, negative 0.1 meters. That's A. This time it's omega squared. So this will be 2 pi over 2.4 seconds and then squared, and then cosine, then 2 pi over 2.4 seconds, and then times that 0.3 seconds. Type that in. So that's just calculator work from there on. Okay. Any questions? Any horrible concerns? Any, oh, please, where's Professor Thompson's? From last semester? Where is he? Huh? I think he's still doing one more class here. I don't know how he wanted to still keep doing astronomy, which is fine because I don't really want to do astronomy. Yeah. Yeah, it could be like that. Maybe more like the homework. Take a look at that. I'm a big theory person. When I started physics, I always thought that I was very conceptual about it. I used concept to